Okay, I don't know what keeps happening to this camera, but it went black again. I'll put the first 3 minutes of the video back up. So here we were talking about, we want to figure out how long does it take the rock to reach half of its maximum height. They gave us S of t, which is half of the max height, and they're asking for t. So we're actually going to be using the original function, 24t minus 0.8t squared. But now we know that S of t is 90. And how do we solve for t? Now obviously this is a quadratic equation. So first off, I'm going to draw a line right here. So first off, we're going to set this up as a quadratic equation. That means I want to subtract 90 to the quadratic side, and I'm going to rewrite it in standard form. So this is negative 0.8t squared minus 24t, I'm sorry, plus 24t minus 90 equals 0. And I want to solve this. Now obviously this is not a factorable problem, so we are going to be using the quadratic formula. So t equals opposite of b plus or minus the square root of b squared minus 4 times a, this has to keep going, times c, and all of that is going to be divided by 2 times a. And of course you do this twice. You do it with all of negative 24 plus all of this divided by this, and then negative 24 minus all of this stuff divided by this, and it has to be done in the calculator, and you end up with two problems at 4.39 seconds and 25.61 seconds. Now remember, another way that you can solve this is basically plug that into the calculator and find the zeros. Okay, so how long does it take the rock to reach half of its maximum distance? Basically, what this is telling us is the rock max was 180 meters. Halfway at 90 meters, it took 4.39 seconds to get to this point, and then it took 25.61 seconds to get to the other 90 meters from the ground, from the moon. Okay, how long is the rock aloft? That means basically how long before the rock comes back to the ground. So when is S of t 0? So you set this up, 24t minus 0.8t squared equals 0. And you solve this. Now because this is set equal to 0, we can take out a t. So this is 24 minus 0.8t equals 0. 0 product property, t equals 0. And here t equals 30. All right, so it's obviously, it's the rock, the time is 0 when the rock starts off at 0 meters, but that's not what I'm asking. This question is asking how long is the rock in the air before it comes back down to 0. So I don't care about this 0, I care about that 0, and it is 30 seconds. So how long is the ball in the air? 30 seconds. Okay? All right, next problem. The velocity of a body is v of t equals 2t cubed minus 9t squared minus 5 meters per second at a time. Find the body's speed and velocity each time the acceleration is 0. So I'm going to start off by finding the velocity. Okay? When acceleration is 0. So when is the acceleration 0. Okay, so first off, we need to actually find the acceleration. Correct? Give me just a second. Okay. So first of all, we need to find acceleration, because we have to take acceleration and we have to set it equal to 0. And remember, to find acceleration, we need to find the second derivative, right? Now the first derivative is what? I'm just going to write it right here. So my first derivative is velocity, and that's going to be 6t minus 18, 6t squared minus 18t. So my second derivative is acceleration, and that's going to be 12t minus 18. And the question is when is acceleration 0? So the first thing I have to do is solve 12t minus 18 equals 0. We add 18, divide by 12. So t equals 1.5 seconds. So acceleration is 0 at 1.5 seconds. So now that I figured out when acceleration is 0, I can find the velocity, right? And the velocity is, I've already figured it out. Velocity is this function. And the question is, v of 1.5 is equal to 6 times 1.5 squared minus 18 times 1.5. Okay? And you can solve that. Right now I don't have a calculator and I am in a rush, so I'm going to let you guys figure this one out. You can tell me what it is tomorrow. Okay? So that is the velocity at 1.5 seconds. And then the speed, remember, is just the absolute value of the velocity. And you are going to actually end up with a negative number here. So the only difference is that whatever you get here at 1.5 seconds, the answer is going to be the absolute value of that. So you guys can figure that out and tell me what it is tomorrow. All right. A particle moves on a number line. The position of p as the function of time is given by the graph below. So s of t is given by this graph. Each one of these ticks measures as 1. So this is 1, 2, 3, 4, 5, 6, 7, 8. So it goes all the way to 6. And then this is also 1, 2, negative 1, negative 2. So this is the particle moving. Okay, it's given by, at t seconds, it's at 0 centimeters. At 1 second, it goes to 2 centimeters. At 2 seconds, it's at 2 centimeters, and so on and so forth. So the question is when is p moving to the left? So p is moving to the left when the slope is negative. Because you can tell that the distance is decreasing, correct? So instead of going forward 1, 2, 3, it's actually going now backwards 4 centimeters. So it's going backwards 4 centimeters. So when is the slope negative? The slope is negative between 2 and 3. So between 2 and 3, and they are not included. And between 5 and 6. So when is it moving to the right? The ball is moving to the right when the slope is positive. And the slope is positive from 0 to 1. And that is basically it. All right, the next part says to graph P's velocity and the speed below. So if you remember, velocity means derivative, and derivative means the slope. So basically, t is still the same, and here we're going to be graphing the slope. So the slope from 0 to 1 is rise, which is 2, and we're running 1. So the slope from 0 to 1 is positive 2. So from 0 to 1 is going to be 2. But remember, this is a corner, so it's not differentiable, so there's no slope at that corner. Now, from 1 to 2, what is the slope? 0. So from 1 to 2, the slope is 0. Okay, from 2 to 3, the slope here is actually negative, and we are basically, based on this, okay, if I try to find the slope between these 2 points, its rise is 1, 2, 3, 4, and we're running a half. So the slope is 4, okay, but negative 4. So here's 1, 2, 3, 4, so that's 2. So from 2 to 3, my slope is negative 4. Okay, then my slope from 3 to 5, so there's 4, there's 5, is 0 again. So from 3 to 5 is 0 again. And then my slope from 5 to 6, we are going down to running 2. So it's negative 2 divided by 2, which is 1. So from 5 to 6, it's 1. Okay? And then the second one is we are going to graph the speed. And here is the t seconds. And remember, the speed is just the absolute value of the velocity. So the only difference is here, everything is staying the same except this guy is going to go up. Okay, and I'll make sure that you guys did this right tomorrow, so I'm not going to graph it here. But this, same. 0, same. This is the same. Oh, and I did this wrong because that should have been down here. I'm sorry. So these two are actually going to get moved up to the positive. So instead of being negative 4, it's going to be graphed at positive 4. Instead of being negative 1, it's going to be graphed at negative 1. And I'll let you guys do that on your own. Okay. Cost of production. And I have to finish this in 5 minutes, and then, well, whatever I don't finish in this video note, I'll add another 5-minute video later. Okay, cost of production. C of x is a function of a number of units produced. marginal cost of production is the rate of change, so it's the derivative of the cost with respect to the level of production, so it's the derivative. Sometimes the marginal cost of production is loosely defined to be the cost of producing one more unit. So if I was producing 5 units, that's kind of telling me approximately what the cost would be to produce 6 units. Okay, and we'll talk about that in a second. So suppose the weekly revenue from the selling X custom-made desks is this. So R of X is equal to 2,001 minus 1 over X plus 1. So I want you guys to graph this, okay, because the graph for the problems that we're doing, it's not really important. And you can graph this on your graphing calculators, and don't forget to label your X and your Y. So your X is the number of desks, and then your Y is the revenue, okay, the weekly revenue, okay? So we want to find the marginal revenue when X desks are sold. Basically, all that means is we want to find R prime of X. So we want to find d dx of this guy. So before I can find the d dx, I want to distribute. Okay, I want to try to simplify this as much as possible. So I'm going to distribute 2,000 minus 2,000 over X plus 1. So I'm going to find the derivative of that function right there. So what's the derivative of 2,000? It's 0. And then minus, okay, the derivative of this guy, if you remember, we're going to use the quotient rule. So I'm going to put this in a big parenthesis for now. And it's going to be the bottom, X plus 1, times the derivative of the top, which is 0, minus the top times the derivative of the bottom, which is 1. So when this cleans up, that negative and that negative, well, what happens to this thing? It actually ends up being 0. And then this negative and this negative make, oh, almost forgot, all of that is divided by X plus 1 squared. So this negative and this negative make this guy a positive. So that's just going to be 2,000 over X plus 1 squared. So that is the function of the marginal revenue. Now we're going to estimate the increase in revenue that will result from increasing production from 5 desks a week to 6 desks a week. Now remember, just right now we said that basically the marginal cost of production is loosely defined to be the cost of producing one more unit. So if we used R prime of 5, that's like figuring out what it would cost to increase our production by one more unit. So you plug this in. So I would have to increase cost by 55 $55.60 to make 6 desks a week. All right, last one. We want to find the limit. You know what? Let's just leave this for tomorrow because we have to look at the graph. And like I said, I am running a little bit late to pick up my children. So let's leave this for tomorrow because we have to look at the graph that you've graphed on your calculator to interpret this number. And then the last two parts is the sensitivity to change and the free fall constants. Basically, they're just definitions. So let me write them tomorrow because I have to run. All right, enjoy.